In the second leg of lecture 11, we want to look at phasors. Let us consider a rotating vector of magnitude A rotating at angular speed omega. If the vector was horizontal at time 0, then the angle that it makes with the horizontal axis at any other time is omega t. The vertical projection of the vector is A sine omega t. This is the general expression for AC with a phase angle of 0. If we plot the vertical projection against time, we obtain a sinusoidal waveform. Therefore, a rotating vector can be used to represent and model AC. Representing an AC waveform using a rotating vector is known as phasor representation. A phasor is defined as a snapshot of the radius vector at time t equals 0. The angle that the phasor makes with the horizontal axis is equal to the phase angle. The appearance of a phasor is similar to the appearance of a complex number in a complex plane. Therefore, a phasor can be modeled as a complex number. It can thus be expressed in polar form using magnitude and phase angle, or in rectangular format using real and imaginary components. This means that AC voltages and currents can be represented using complex numbers. Since AC values are quoted as RMS values, the phasor magnitude is redefined to be equal to the RMS value of the voltage or current being represented. This allows methods used for analyzing DC circuits to be extended with great ease into methods for analyzing AC circuits. We have an exercise here. I will do 2 questions for you. The rest you will do on your own. Solution for 1C. First, you convert the cosine into a sine. We obtain the expression 45 sine 377t plus 105 degrees. From that expression, the phase angle is 105 degrees. The RMS value is 45 over root 2, which is 31.82. Therefore, in phasor form, the waveform is 31.82 at an angle of 105 degrees. Solution for 2B. From the given phasor, the phase angle is minus 70 degrees. The peak value is 115 times root 2, which is 162.6. The angular frequency omega is 2 pi by 60, which is 377. Therefore, the sinusoidal expression for the voltage is 162.6 sine 377t minus 70 degrees. A phasor diagram is a diagram that shows the relative magnitudes and relative positions of various phasors of the same frequency. Let's illustrate using some examples. In the first example, we have a series circuit made up of 2 components. We are given the respective voltages across the components as sinusoidal expressions. We want to find the input voltage, draw a phasor diagram showing the relationships between the voltages, and then sketch the waveforms on the same axis. In phasor form, the voltages VA and VB are 35.35 at 30 degrees and 21.21 at 60 degrees respectively. The input voltage is the sum of the two voltages VA and VB because this is a series circuit. Therefore, in phasor form, the input voltage is 54.76 at 41.17 degrees. In time domain, the input voltage is 77.43 sine 377t plus 41.17 degrees. And this is the phasor diagram. We can see the phasors for the three voltages. The phasor for VA makes an angle of 30 degrees with the horizontal axis. The phasor for VB makes an angle of 60 degrees with the horizontal axis. The phasor for the input voltage makes an angle of 41.17 degrees with the horizontal axis. We can observe that the phasor for the input voltage is a vector sum of the phasors for VA and VB. In the second example, we are given a parallel circuit made up of two components. We are given the total current to the circuit and the current in one of the components. We want to determine the current in the other component. Draw a phasor diagram showing the relationships between the currents and then sketch the waveforms on the same axis. In phasor form, IT equals 84.84 times 10 to the power minus 3 at 60 degrees. I1 is 56.56 times 10 to the power minus 3 at 0 degrees. By Kirchhoff's current law, I2 equals IT minus I1, and we get a value of 74.82 times 10 to the power minus 3 at 100.89 degrees. In time domain, I2 equals 105.8 times 10 to the power minus 3 sine omega t plus 100.89 degrees. And this is the phasor diagram. It shows the phasors for the three currents. We can observe that the phasor for I2 is the vector difference between the phasor for IT and I1. Impedance is a measure of how much a circuit or circuit element will impede or hinder the flow of AC through it. From the Ohm's law, opposition is equal to voltage over current. Now, voltage and current are modeled as complex numbers. Therefore, the opposition comes out as a complex number. This means that opposition to the flow of AC through an element or a circuit is modeled as a complex number. This is the reason why we commonly refer to it as complex impedance. The symbol for impedance is Z and the SI unit is the ohm. Let's look at the impedance of a pure resistance. If the voltage across a pure resistance R is expressed as Vm sin omega t, then according to Ohm's law, the current through the resistance is Vm sin omega t over R. This can be expressed as Im sin omega t, where Im is Vm over R. We notice that for a pure resistance, voltage and current are in phase. To obtain the impedance, we express the voltage and current in phasor form and then apply the Ohm's law. We obtain a complex number with a magnitude equal to the resistance value and an argument equal to 0. Therefore, the impedance of a pure resistance is a real number equal to the magnitude of the resistance. When it is taken into the complex plane, it is a fixed radius in the positive real axis of the plane. Let's proceed to the impedance of a pure inductance. Suppose the current flowing through a pure inductance L is expressed as Im sine omega t. From the relationship between inductor voltage and inductor current, the expression for the voltage across the inductance is obtained as omega L sine omega t plus 90 degrees. This can be expressed as Vm sine omega t plus 90 degrees, where Vm is equal to omega L. From the expressions, we notice that for a pure inductance, voltage leads current by 90 degrees. Let's express voltage and current in phasor form and then apply the Ohm's law. We obtain the impedance of the inductance as being equal to omega L at 90 degrees, which is equivalent to J omega L. Therefore, the impedance of a pure inductance is a positive imaginary number. If it is taken to a complex plane, the impedance is a fixed radius in the positive imaginary axis of the plane. The impedance of an inductance is called inductive reactance. The symbol is XL and the units are the ohms. Let's go to the impedance of a pure capacitance. Suppose the voltage across a pure capacitance C is expressed as Vm sine omega t. From the relationship between capacitor voltage and capacitor current, the expression for the current through the capacitance is obtained as omega C sine omega t plus 90 degrees. This can be expressed as Im sine omega t plus 90 degrees, where Im is equal to omega C. From the expressions, we notice that for a pure capacitance, the current leads the voltage by 90 degrees. Let's express the voltage and current in phasor form and then apply the Ohm's law. We obtain the impedance of a capacitance as being equal to 1 over omega C at 90 degrees, which is equivalent to minus J over omega C. Therefore, the impedance of a pure capacitance is a negative imaginary number whose magnitude is equal to 1 over omega C. When taken into the complex plane, the impedance is a fixed radius in the negative imaginary axis of the plane. The impedance of a capacitance is called capacitive reactance. The symbol is Xc and the units are the ohms. In this exercise, we want to find the sinusoidal expression for the voltage across the given element if we are given the expression for current. I'll leave this exercise for you to do on your own. Here is another exercise. In each question, we are given the sinusoidal expressions for voltage and current. We are required to determine the type of element involved and then calculate the primary quantity that defines the element. I will do question 2 for you and you will do the rest on your own. Let's look at the solution for question 2. From the given expressions, we notice that voltage leads current by 90 degrees. Therefore, the element involved is an inductance. From the peak values of voltage and current, we can obtain the magnitude of the reactance. We obtain it as 200 ohms. From the frequency and the inductance, we can also determine the magnitude of the reactance. In this case, we obtain it as 377 L. Let's equate the two values and solve for L. We obtain the inductance as being equal to 0.53 henries. Generally, a circuit consists of an interconnection of resistances and reactances. The overall impedance of the circuit can be expressed in the form R plus Jx, or equivalently, magnitude of Z at an angle theta t. R is the net resistance of the circuit, X is the net reactance of the circuit, theta t is called the impedance angle. It normally lies in the range minus 90 degrees to plus 90 degrees. The impedance angle is equal to the angle by which the applied voltage will lead the current. For each question in this exercise, we are given sinusoidal expressions for voltage and current. We are required to determine the impedance and calculate the net resistance and the net inductance or capacitance. I will do question A for you and you will do the rest on your own. Let's look at the solution for question A. From the expressions, we notice that voltage leads current by 60 degrees. Therefore, the circuit is inductive. In other words, it is made up of a net resistance and a net inductance. From the peak values of voltage and current, the magnitude of the impedance is calculated as 22 ohms. Therefore, the complex impedance equals 22 ohms at 60 degrees. In rectangular format, it is 11.0 plus J19.1. This means that the net resistance of the circuit is 11 ohms and the magnitude of the net reactance of the circuit is 19.1 ohms. I will leave you to calculate the inductance on your own. An impedance diagram is a complex plane in which impedances are shown. Resistances are in the positive real axis, inductive reactances are in the positive imaginary axis, capacitive reactances are in the negative imaginary axis. Admittance is a measure of how well an element or a circuit will admit or allow an AC current to flow through it. It is equivalent to the reciprocal of impedance. The symbol for admittance is Y, and the SI unit is the Siemens. Susceptance is the reciprocal of reactance. It is formally defined as a measure of how susceptible a reactive element is to the passage of current through it. The symbol is B and the SI unit is the Siemens. For an inductance, susceptance is equal to 1 over omega L at an angle of minus 90 degrees, which is equivalent to minus J over omega L. For a capacitance, susceptance equals omega C at 90 degrees, which is equivalent to J omega C. Here is another exercise. For each question, we are given the sinusoidal expressions for voltage and current. We are required to determine the admittance. I'll leave these questions for you to do on your own. An admittance diagram is a complex plane on which admittances are shown. Conductances are in the positive real axis. Capacitive susceptances are in the positive imaginary axis. Inductive susceptances are in the negative imaginary axis. I recommend that you do these questions from chapter 8 before you proceed to the next lecture.